in last few lectures we have been investigating the behavior of uniform plane wave across the dielectric media. We studied two cases, one with parallel polarization and other with perpendicular polarization, and saw their reflection and transmission across a dielectric boundary. We also investigated a special case, what is called total internal reflection across the dielectric boundary. Today we discuss the important aspect of electromagnetic wave, that is the polarization across the dielectric interface. So, in this lecture essentially we take a wave which is arbitrarily polarized, that means its electric field vector makes an arbitrary angle with respect to plane of incidence. Also it might be varying as a function of time, and then we will see how this behavior changes when the wave is reflected from a dielectric interface. So, the problem to investigate here is that if the incoming electromagnetic wave had certain polarization, what would be the polarization of the reflected wave and what would be the polarization of the transmitted wave. As we discussed earlier, a arbitrary state of polarization can be decomposed into two orthogonal polarization, and in this case we take two orthogonal polarizations which are linearly polarization, one which is perpendicular to plane of incidence and other with parallel to the plane of incidence. So, in general an electric field when the wave is incident in the media interface can be represented by the vector sum of two electric fields, that is the perpendicular and parallel polarization. So, we have in this case now the incident wave let us say this is denoted by E I and this is a vector quantity. So, this is now given by the incident wave for parallel polarizations. So, this is E I with parallel polarization plus you have the incident wave for perpendicular polarization, again a vector quantity, and these two depending upon the state of polarization, these two orthogonally linearly polarized waves might have a phase difference. So, let us say that is denoted by e to the power some j phi. So, we have two electric fields now, one which is in the plane of incidence, other which is perpendicular to plane of incidence, and the phase difference between these two is phi when the wave is incident at the dielectric interface. So, the situation is if this is the dielectric interface, the wave is incident on this. So, I have two components now, one is this electric field which is given by E I parallel, other one is the electric field which is perpendicular to this which is given by E I perpendicular e to the power j phi. So, any now arbitrary state of polarization is a combination of these two fields, and if we separately solve the problem as we mentioned earlier for the two polarization, the parallel and perpendicular, then we can combine them back to find out the polarization of the reflected and the transmitted wave. So, in general again the transmitted wave also will have two electric fields and the reflected wave also will be having two electric fields. So, what we do essentially we find out now the reflected field for the parallel polarization and the transmitted field for parallel polarization, and same we do for perpendicular polarization, and then we combine them together. So, in general then we can get the reflected wave that is let us say is denoted by E R, that will be equal to E R parallel plus E R perpendicular. And if I denote the reflection coefficient for the parallel and perpendicular wave, with gamma parallel and gamma perpendicular as we have done earlier, then this quantity can be written as gamma parallel EI parallel plus gamma perpendicular EI perpendicular e to the power j phi. Similar thing I can do for the transmitted wave also. Where Et, the transmitted wave, total wave, will be again a combination of the two polarizations. So, that is tau parallel EI parallel plus tau perpendicular EI perpendicular e to the power j phi. Now, depending upon the case whether it is a normal reflection or total internal reflection, these quantities gammas, they could be either real quantities or they could be complex quantities. We have seen earlier, if you take a normal reflection, then the reflection coefficient is a real quantity and it could have a positive or negative sign. But if you take the total internal reflection, then these quantities gamma, they become complex, though their magnitude becomes equal to 1. So, now we are having various possibilities, and that is what essentially we will see some special cases. That suppose if the wave was linearly polarized and if the reflection was a normal reflection, what would happen to polarization? If it is total internal reflection, then what would happen to polarization, and if the wave was circular, what would happen, and so on. So, let us take now some special cases. That first case, let us say if the wave is linearly polarized. That means the electric field vector does not change the direction as a function of time for the incident wave. It makes some angle like that with the plane of incidence. So, if this is the plane of incidence, that is the angle which the electric field vector makes, but this direction remains same independent of time. And as we know, a linearly polarized wave is represented by combination of two orthogonal polarizations with no phase difference. So, if the wave is linearly polarized, then the phase difference between these two components is 0. That means for this case the phi is equal to 0. Once we have this, then of course we can investigate now two cases, whether it is normal reflection or the total internal reflection. So, if I consider the normal reflection case, your gamma parallel and gamma perpendicular are real. So, if this quantity is real and if this phi, this angle is 0, essentially these quantities which are these two electric field, this one and this one, if the initial phase difference phi is 0 between them and if the reflection coefficients are real, the phase difference between them again remains 0 or 180 degree depending upon the direction of the electric field. But in both the cases, the polarization remains linear polarization, because the 180 degree phase shift essentially means reversal of the electric field. So, the orientation of electric field will change, but the polarization will remain linear polarization. So, in this general case, phi parallel and phi perpendicular are real, and magnitude of phi parallel is not in general equal to the magnitude of gamma perpendicular. So, that means a linearly polarized wave will remain linearly polarized because the phase difference between the two components is not going to change, but their relative amplitude for the reflected wave might change depending upon whether this condition is satisfied, or in some very special case these two are equal, then the two reflected amplitudes also will be same. That means the ratio of the two components of the reflected wave are not same as it was for the incident wave. That means the direction of the electric field vector now is changed. That means the orientation of linearly polarized wave will change, but the wave will remain linearly polarized. So, in this case we have an important thing, that is wave remains linearly polarized, but its orientation might change. So, plane of polarization might change depending upon when these two are not equal, but the nature, linearly polarized nature of the wave will be maintained if this is a normal reflection. On the other hand, if I am having total internal reflection, then these quantities gamma parallel and gamma perpendicular are not real. These quantities are now complex quantities, but the magnitude of these two are equal now. So, in this situation gamma parallel and gamma perpendicular are complex, but gamma parallel is equal to gamma perpendicular is equal to 1. So, the ratio of the two electric fields, whatever these quantities now mod of them are 1, but these quantities are now complex. So, the phase difference between these two components is going to change, though the amplitude ratio which was for the incident wave, same thing is maintained for the reflected wave. But since now the phase difference could be arbitrary, in general we will get a polarization which will be elliptical polarization. So, in this case in general a polarization, linear polarization changes to elliptical polarization. So, the important conclusion is, if the wave is linearly polarized and if the reflection is ordinary reflection, then the linear polarization of the wave remains unchanged, whereas if the reflection is total internal reflection, then the wave becomes an elliptically polarized wave. The same thing essentially applies to the transmitted wave also, because in this case also you are going to get the similar kind of combinations. So, a linearly polarized wave will remain linearly polarized after transmission also, because the tau parallel and tau perpendicular will be the real quantities for the normal reflection. We can take another special case, that is the circular polarization. That if the incident wave is circularly polarized, then what will happen to this wave at ordinary reflection and at total internal reflection. So, as for circular polarization, as we know that these two components EI parallel are equal to EI perpendicular, the two components are equal, and also the phase difference between them is plus minus pi by 2. So, the phi in this case will be plus minus pi by 2. So, now in general when the wave is incident of this type, and if I have ordinary reflection, again your gamma parallel magnitude is not equal to gamma perpendicular, but these quantities gamma parallel and gamma perpendicular are real. That means the phase difference between the reflected waves still remains pi by 2 plus minus pi by 2, but the amplitude ratio for the reflected wave for perpendicular and parallel will not be equal, because these two coefficients are not equal. So, in general then we have in this case ER parallel is not equal to ER perpendicular, but the phase difference between these two is still plus minus pi by 2, and phase difference between ER parallel and ER perpendicular is plus minus pi by 2. And we have seen in this case that when the amplitudes are not equal, but if the phase difference between them is 90 degrees, the wave becomes elliptically polarized, but in this case the major and minor axis align with the coordinate axis for the ellipse. So, in this case when the wave was incident on this like that, initially it was circularly polarized, it was rotating like this. Now, after reflection the two amplitudes are no more equal, so the wave has become elliptically polarized, but since the phase difference between them is 90 degrees still for ordinary reflection, the major and minor axis of the reflected wave ellipse will lie in the plane of incidence and perpendicular to plane of incidence. So, you will have the ellipse which will be either drawn like that or ellipse which will be drawn like that, but the axis which the major axis makes with the plane of incidence will be either 0 or will be 90 degrees. So, the tilt angle for the ellipse with respect to plane of incidence will not be arbitrary, but it will be either 90 degrees or it will be either 0. So, in this case essentially we get the axial ratio will depend upon these quantities, but the tilt angle is 0 or pi by 2 with plane of incidence. What will happen to total internal reflection? If I take total internal reflection, then the magnitude of these will be equal, but the phase difference will not remain pi by 2. So, in general again I will get a wave which will be elliptically polarized. So, a circularly polarized wave at ordinary reflection will become elliptically polarized with its tilt angle 0 or pi by 2 with respect to plane of incidence, or a total internal reflection, this wave in general will become an elliptically polarized wave. Of course, if I have a wave which is in general incident wave is elliptically polarized, then in general we can make a statement that its state of polarization will change, and depending upon the parameters, right, even elliptically polarized wave might become circularly polarized, right, or it can even become linearly polarized. So, essentially what we see from this exercise that the media interface can be used to alter the state of polarization of an electromagnetic wave. That is the important message essentially we should get from here. So, that means if I have a certain state of polarization for the incoming wave, then by launching the wave at an arbitrary angle, we should be able to change the state of polarization to the desired state. One of the special cases of this is that if the wave is some arbitrarily polarized wave, is it possible that the reflected wave will be linearly polarized? Because there are many applications where we require a wave which is linearly polarized. The sources which we might have may not generate intrinsically a linearly polarized wave. So, we look for some mechanism by which an arbitrarily polarized wave can be converted into a linearly polarized wave. And since we saw that the dielectric interfaces can change the polarization of the electromagnetic wave, this could be one of the interesting situations to investigate whether an arbitrary polarization can be converted into a linear polarization. So, let us now take the special cases that if the wave is incident at a certain angle. We have investigated again two cases. One was the perpendicular polarization, for which the reflection coefficient was given by this, and we also investigated the parallel polarization, for which the reflection coefficient was given by that. One can now ask a question, for a given parameter, if this quantity becomes 0 for parallel polarization, or this quantity becomes 0, that means if the reflection coefficient becomes 0, then whatever wave is incident on the dielectric interface is completely transmitted to the second medium. There is no reflection at the boundary. That is what the reflection coefficient 0 would mean. That means now if I put a perpendicularly polarized wave at an angle when this quantity becomes 0, then this perpendicular polarization will completely pass through the medium, there is no reflection. Similarly, if I take a wave which is parallelly polarized, and if I launch at an angle which satisfies this condition, then the parallel polarization will completely pass through and there will not be any reflection for this wave. So, now if I have a arbitrarily polarized wave and if I launch at an angle which satisfies this condition, then parallel polarization will pass through, but this same condition, the perpendicular polarization will not completely pass through, so it will have a reflection. So, the reflected wave will have only perpendicular polarization, and same is true for the angle which satisfies this condition, that the perpendicular polarization will pass through and the reflected wave will have only parallel polarization. In both the situation, essentially the polarization will be a linear polarization. So, we have now the interesting cases, that is, for given parameters, look for the angles for which this quantity goes to 0 or this quantity goes to 0, and at those angles one of the polarization will be reflected, but other polarization will be completely transmitted to the second medium. So, a arbitrary state of polarization can be converted into a linear polarization. So, that is what essentially we investigate. So, let us say for parallel polarization, the gamma parallel becomes 0 when eta 1 cos theta I is equal to eta 2 cos theta t. So, this is the reflection coefficient expression. I just equate this to 0. So, when eta 1 cos theta I becomes eta 2 cos theta t, at that point I have the gamma parallel 0. Similarly, for perpendicular polarization, I will have gamma perpendicular is equal to 0 when from this expression the gamma perpendicular goes to 0, that means eta 2 cos theta I is equal to eta 1 cos theta t. And let me remind you, these quantities, the eta 1 and eta 2 are the intrinsic impedance of medium 1 and medium 2. So, eta 1 is square root of mu 1 upon epsilon 1 and eta 2 is equal to square root of mu 2 upon epsilon 2. And then you also have the Snell's law, which relates theta I and theta t. We are considering only the ordinary reflection. So, by applying the substituting for theta t in terms of theta I, essentially we can get the angles theta I, the angles of incidences for these two polarization, where the reflection coefficient would be 0. So, if I do substitute and then do some small algebraic manipulation, essentially we get the expression for this, that would be tan of theta, let me call that some b perpendicular. I will explain what this theta b means. That is equal to beta 2 upon eta 1, eta 2 square minus eta 1 square upon beta 2 square minus beta 1 square square root, and for parallel polarization I will get tan of theta b parallel, that is equal to beta 2 upon eta 2, eta 1 square minus eta 2 square upon beta 2 square minus beta 1 square square root. This angle at which the reflection coefficient go to 0 is called the Brewster angle. So, when the parallel polarization goes to 0, we say this is the Brewster angle for parallel polarization. When perpendicular polarized reflection coefficient goes to 0, we will say that angle is the Brewster angle for perpendicular polarization. In general, if you take a medium which could be even magnetic medium, then the Brewster angle for both polarization exists. So, at that Brewster angle for parallel polarization, the reflected wave will have only perpendicularly polarized wave, and for a Brewster angle which is for perpendicular polarization, the reflected wave will have only parallel polarization. So, B essentially this quantity is here, theta B is called the Brewster angle. So, theta b perpendicular is the Brewster angle for perpendicular polarization, and theta b parallel is the Brewster angle for the parallel polarization. So, at this angle the parallelly polarized wave will completely get transmitted. For this angle the perpendicular polarized wave will get completely transmitted to the second medium. Now, since we know these quantities beta 1 and beta 2, which is beta 1 is square root of mu 1 epsilon 1 and beta 2 will be omega square root mu 2 epsilon 2, and eta 1 and eta 2 we have already got here. So, if you substitute these quantities into the expression for the Brewster angle, we essentially get the Brewster angles for two cases, theta b perpendicular, that will be tan inverse square root mu 2 upon mu 1 mu 2 epsilon 1 minus mu 1 epsilon 2 upon mu 2 epsilon 2 minus mu 1 epsilon 1 and theta Brewster for parallel polarization, that would be tan inverse square root of epsilon 2 upon epsilon 1 mu 1 epsilon 2 minus mu 2 epsilon 1 upon mu 2 epsilon 2 minus mu 1 epsilon 1 square root this angle. So, as we can see, if the medium is general, that means if we have the permeability and permittivity is different for the two media, then both these angles would exist, and at these angles one of the polarization essentially will get completely transmitted to the second medium. However, if I consider only the dielectric media, that means the permeabilities for these two media are same as the free space, then the mu 1 is equal to mu 2. So, if we consider only dielectric media, if we take a dielectric medium, then we have mu 1 is equal to mu 2. So, this quantity will be 1, the mu 1 is equal to mu 2. So, this can be taken out. So, essentially we will get here theta b, the epsilon 1 minus epsilon 2, this epsilon 2 minus epsilon 1. So, this quantity will become an imaginary quantity. So, you can see here, you can take here mu 1 and mu 2 which is same, you can take it common. So, this will become epsilon 1 minus epsilon 2, this will be epsilon 2 minus epsilon 1. So, this quantity will become minus 1. So, you will get this is square root of minus 1, so which is the imaginary angle. What that means is that if we consider only the dielectric media on both sides, if the permeabilities are same, then the Brewster angle for perpendicular polarization does not exist. So, for in this case theta b perpendicular does not exist. So, there is no Brewster angle for perpendicular polarization if we consider the media which are the dielectric media. In this case, the Brewster angle for parallel polarization would exist, because if I take mu 1 equal to mu 2, this quantity will be same. So, this quantity has become 1 now. So, you will get theta b parallel which will be tan inverse square root of epsilon 2 upon epsilon 1. So, in this case theta b parallel will be equal to tan inverse of square root epsilon 2 upon epsilon 1. And since the tan of theta has a range from minus infinity to infinity, so it can take any possible value from 0 to infinity. For any dielectric media, any values of epsilon 2 and epsilon 1, I will always get a Brewster angle. So, we have an important conclusion that if I consider the dielectric media interface, then the Brewster angle for parallel polarization always exists, but for perpendicular polarization there is no Brewster angle. And this we can see physically as follows: why for perpendicular polarization it does not exist and for parallel polarization it exists. That let us say this is the dielectric interface, and let us say the electric field was perpendicular to the plane of incidence. So, it was like this. Now, irrespective of what is the direction of the incident wave, this field is always going to be like this and its amplitude is fixed. So, when I apply the continuity of the electric fields, I will get this field plus the reflected field plus the transmitted field, sum of these two should be equal to this field. And since these amplitudes are not depending on the launching angle, you will never get a condition where sum of these two will become exactly equal to this. So, I always will need the reflected wave to satisfy the boundary conditions at the interface. Whereas, if I consider a parallel polarization which is like this, then the component which has to satisfy the boundary condition is a tangential component. So, if I take a wave like that and this is the electric field, this component essentially has to satisfy the boundary condition. So, if this angle is theta I, this angle is theta t, then the electric field will be like that, but this is the component which will be tangential component to the interface. So, this is theta I, this will be theta I, this will be theta t, this is electric field E t, this is E I. The boundary condition has to be satisfied by the tangential component of electric field, and since the tangential component is a function of theta I, this is E I cos of theta I, and this is E t cos of theta t. As we change the angle, it is possible at some particular angle these two components become equal. So, E I cos theta I, if it becomes equal to E t cos theta t, then I do not require electric field due to the reflected wave to satisfy the boundary condition. That means, this wave will not be needed anymore to satisfy the boundary condition at the interface. So, when this condition is satisfied, that E I cos of theta I is equal to E t cos of theta t, that time this wave is absent, I do not have any reflection. So, the wave which is incident on this is completely transmitted to the second medium. So, in this case, since the tangential component varies as the angle of incidence, at certain angle these two components just become equal, and then I do not have this third component to satisfy the boundary condition. However, for perpendicular polarization this situation is not there, because I have this electric field which is like this, which does not depend upon the direction of the wave. So, we always require this field so that sum of these two becomes equal to the field in the second medium. Of course, if the media was a magnetic media and if the permeabilities for the two media were not same, then argument which you have for electric field will be applicable to the magnetic fields, and then we will have Brewster angle for the perpendicular polarization also. But if you take the media which are dielectric media, then the Brewster angle would exist only for the parallel polarization, and the Brewster angle for perpendicular polarization would not exist. I can write this in terms of the refractive indices also, because we know square root of the relative permittivities is called the refractive index. So, this is also equal to tan inverse of the refractive index of medium 2 divided by refractive index of medium 1. Generally, since we deal with the dielectric media, we can say that we have the Brewster angle for the parallel polarization, and one can make use of this Brewster angle for converting a arbitrarily polarized wave into a linearly polarized wave. So, now let us say if the wave was arbitrarily polarized like this, we can decompose this wave into the parallel polarization and perpendicular polarization. If the wave is launched at the Brewster angle, then the parallel polarization will be completely transmitted to the second medium. So, there is no reflection for parallel polarization, but for that angle, since this is not a Brewster angle for perpendicular polarization, the perpendicular polarized wave will get reflected. So, in the reflected wave we will have a polarization which will be only perpendicular polarization. So, if I take now a media interface that and launch this ray at the Brewster angle for parallel polarization. So, in this case we have both the electric fields, here this is E I parallel, this is E I perpendicular, and this angle now is theta b parallel. So, the reflected wave which we will get from here will be having only perpendicular polarization. So, this wave is perpendicularly polarized. So, you get only ER perpendicular, because parallelly polarized wave is completely transmitted to the second medium. So, in the second medium we will get a wave which is in general an elliptically polarized wave, because we have both the components this and this. So, this will be ET parallel, ET perpendicular, but for reflected wave we will have only perpendicular polarization, which is ER perpendicular. That means, without worrying about what is the state of polarization of the incoming wave, whether it is linearly polarized at some arbitrary angle, or it is elliptically polarized or circularly polarized, if the wave is launched at the Brewster angle, then the reflected wave will have a polarization which is linear polarization, and the orientation of that will be perpendicular to the plane of incidence. So, for any arbitrarily polarized wave, the reflected wave will be linearly polarized like that. That is the reason this angle is also called the polarizing angle, because at that angle, if the wave is launched, the wave reflected wave is polarized in the linear polarized fashion. So, this angle is also referred to as a polarizing angle. So, at polarizing angle, if the wave is launched at the dielectric interface, the reflected wave is always linearly polarized wave. It finds application in polarizing the light beam in the lasers, and internally if the polarization was arbitrary, then we can always use the concept of Brewster angle, so that the reflected wave from the boundary is always linearly polarized. So, what we conclude from this discussion essentially is that by using the dielectric interfaces, one can change the state of polarization of an electromagnetic wave. This has been routinely done for the optical beams, but even at other radio frequencies, one can make use of this phenomena for changing the state of polarization of an electromagnetic wave. We will see little later, when we talk about the reflection and refraction from the conducting boundaries, how the state of polarization will get affected from the incident to the reflected wave. We have seen here that if you take a circular polarization, then it may become elliptical polarization, or it could become linear polarization, and so on. In case of conducting boundaries, the case are a little simpler, but you will find something more interesting phenomena and when we talk about the reflection from those boundaries. So, this essentially gives you an idea of how to make use of the dielectric boundaries for changing the state of polarization of an electromagnetic wave. With this understanding of the dielectric boundaries, now we can ask a general question. Just suppose I do not have now a dielectric boundaries, but suppose I have a general media boundaries. That means the conductivity of the two media are not 0. So, if I take a medium interface in general, where in medium 1 and medium 2 I have permeability mu 1 epsilon 1, and also the conductivity for this medium is sigma 1, but sigma 1 is not infinity, it is not ideal conductor. Similarly, for medium 2 we have permeability mu 2, permittivity epsilon 2, and the conductivity sigma 2. Once we have this, then we have the medium parameters, which we know is the propagation constant and the characteristic impedance or intrinsic impedances of the media. So, we have for this medium your eta 1, which is now square root of j omega mu 1 divided by sigma 1 plus j omega epsilon 1. We have already discussed this earlier. Similarly, for this medium I have the intrinsic impedance eta 2, which is square root of j omega mu 2 upon sigma 2 plus j omega epsilon 2, and propagation constant now is in general, it is not only beta, but it is gamma. So, gamma 1 is equal to square root of j omega mu 1 sigma 1 plus j omega epsilon 1, and gamma 2 is equal to square root of j omega mu 2 upon sigma plus j omega epsilon 2. And now we can write down for this interface, if the wave is incident on this, what will happen to the reflected and transmitted wave of the interface. Recall now, when we solved this problem, essentially we satisfied the boundary condition at the interface, and we had satisfied the boundary condition for the tangential component of electric field and tangential component of magnetic fields. Even if the conductivity is non-zero, but it is not infinite, still we do not have surface currents here, and because of that I can still apply the boundary condition which we applied for the dielectric cases. So, the expression which we got for transmission and reflection coefficients, they are still valid for this case or the parallel case, except now that you have to change these quantities eta 1 and eta 2 appropriately by these quantities, where you have taken the conductivity into consideration. So, since we are still applying the boundary condition which we applied for dielectric media, nothing has changed in the analysis. In fact, we got a similar expression, only these quantities eta 1 and eta 2 have become complex, and because of that, in general, even for the normal or the ordinary reflection also, this quantity reflection coefficient has become complex, and same will happen for the transmission coefficient also. So, in general media, which is the lossy media, the analysis remains exactly identical, and we can use the same expression which we derived for dielectric media by replacing eta 1 and eta 2 by this complex quantity, which takes into account the conductivity of the media. So, this we can say is a lossy media interface. So, in fact, appropriately choosing this intrinsic impedances of the media which are complex, the analysis for lossy media is identical to what we have done for dielectric media. However, there may be some conceptual questions one may ask at this point, if the medium was lossy, that in the presence of loss, this quantity gamma is a complex quantity, that means it has a real part which gives you the attenuation constant. Same is true for this one. Earlier, when the plane wave was incident on the media interface, it did not matter from where the wave was originated, since the wave amplitude does not change, even if it had travelled infinite distance, the amplitude of the wave is same when it is incident on this medium. However, if we assume that the uniform plane wave was originated at an infinite distance from the interface, and if this quantity is complex, then the wave amplitude exponentially decreases as it travels. So, after travelling an infinite distance, the amplitude which reaches here would be 0. Similarly, if I consider that the wave had a finite amplitude at this point and is a plane wave, so which if it has started from minus infinity and travelled this distance, then it should have had an amplitude which is infinite at the infinite distance from this plane. So, it would mean that in case of lossy medium, probably you will require infinite energy to start with. If the wave starts from infinity, then when the wave reaches here, it will have a finite amplitude. Well, this is a very hypothetical situation. Without getting into the issue where the wave was actually originated, we can address this question only saying that if the wave, when it reaches to the media interface, has a certain amplitude, then the amplitude of the reflected wave just this side of the media interface and just this side of the media interface will be given by the reflection and transmission coefficients which we have got here. When the wave travels now the backwards from here, because there is a loss in the medium, this wave will slowly attenuate. This wave amplitude will be growing, because if it had certain amplitude here, it would be exponentially growing as you go opposite to the wave propagation, and this wave which is transmitted to the second medium also will be exponentially decreasing in the amplitude. So, this situation is very straightforward, that in this case you are having a travelling wave with a propagation constant which is this. So, wave travels with slowly decreasing amplitude which depends upon the loss in the medium which is this sigma 2. Whereas, when you come to medium 1, the fields which you are going to see are superposition of the incident and the reflected wave. So, this wave grows as we go away from the interface, this wave decays as we go away from the interface. So, we see superposition of these two, and this case is identical to lossy transmission line, that as we go away from this junction or termination of transmission line, the reflected wave becomes weaker and weaker on a lossy line, and the transmitted wave grows larger. So, essentially as you go away from this interface, you will see the phenomena which will be only travelling kind of phenomena, but when we come close to the boundary, then you will see the interference of these two waves and you will see some kind of a standing wave behavior. So, this is exactly identical to what we have seen for a lossy transmission line. So, to conclude, the analysis of a lossy media interface where the conductivity is finite, but is neither 0 nor infinity. So, that means none of the media are ideal conductors or neither they are ideal dielectrics. The problem can still be handled exactly in the same way as we did for the dielectric media. We can apply the same boundary conditions and we can apply the same expression for the reflection and transmission coefficients. Then substituting appropriately for the intrinsic impedances for the two media, we can get the expressions for the transmission and reflection coefficient for a lossy media.